we already learned that the period of oscillation of a simple pendulum is given by t equal to 2 pi into root of L by G. Here, t represents the period of oscillation we explained just before, and where L is the length of the pendulum and G means acceleration due to gravity. And today's our experimental objective is to get G experimentally, right? Now, what we did here, I mean, if you go further with this equation, if I square this equation, what will happen? T square, right? Equal to, come on, 4 pi square, yes, L divided by G. Yes, so 4 pi square L by G. If you look into this equation, T square is what? 4 pi square divided by G times L. If I write this way, we can see that 4 is a constant, pi is a constant, G is a constant, is it? So that means I can simply write T square is proportional to L, is it? So today in our experimental setup, we took length and the corresponding period. If I have period, of course I can find period T square, right? That means today I have a set of L and corresponding T square. Look into this equation. We know that T square is proportional to L. And the way that we did in our previous experiment, if I'm going to plot this, I mean, if I plot T square in the y-axis and L in the x-axis, what kind of a graph we are going to get? Yes, you are right. We will get a straight line. Yes. And once I fit this into a straight line, and the computer can give me the slope of this, right? And what will be the slope of this? Represents slope equal to what? Can you guess? Look here. I plot this in the y-axis and this in the x-axis. And we know that our equation y equal to mx, right? So y, that means t square, and here 4 pi square divided by g times x. So look at the slope. What is the slope represents? Yes, slope is 4 pi square divided by g. Here comes our answer, right? What is the g experimental then? G is 4 pi square divided by slope. Am I right? So now you can able to find G experimentally. That's all about our experiment, and we are going to do it now.
This setup will be used to study the simple pendulum. This is not a simple pendulum though, because for a simple pendulum, the string or the rod that connects the mass to the axis of rotation should be massless. But in this case, this has a mass, this rod has a mass. Okay, so this is called a physical pendulum, but we will use it to approximate a simple pendulum. Now, first of all, you have to set the length of the simple pendulum to a given value. Now let's say that I'm using the maximum length of the rod as the length of my pendulum. So I have to measure the distance from the axis of rotation to the center of the mass. This is gonna be the length L. Okay. So again, be careful when you do this measurement, because this is where most of the error occurs. Right? So the distance from the center of rotation or axis of rotation to the center of mass. Okay. In this case, it says 34 centimeters exactly. Right? And be careful because this side is in feet and inches. Now this here is a rotary motion sensor which measures the angle of rotation. Okay. So the computer uses this data to plot a graph of position versus time, and also angular velocity versus time. Now, furthermore, for simple harmonic motion, the angle for the maximum displacement from equilibrium, this angle should be small in order for the motion to be a simple harmonic motion, right? So if you use a large angle, and remember this is a physical pendulum, we're trying to approximate the motion of a simple pendulum. Add to this a combination of a large angle, this will introduce a lot of uncertainty to your data. So for this reason, be sure to always use small displacements like this. Now, as you can see, this is a periodic motion. We define the period of any oscillation as the time required to make one full cycle. Okay? The full cycle for a motion like this can be defined, for example, let me stop it, from the maximum to the other maximum and back to the same point. This is a full cycle. So the time required for the pendulum to go from here to the other extreme and back to the same point, this is called the period of oscillation. Okay? The period of oscillation, of course, because it's a time, has a unit of second. The frequency, on the other hand, is defined as the number of cycles this pendulum makes per second. There is another quantity that you should be aware of, which is called the angular frequency. The angular frequency is 2 pi times the frequency of the motion. Okay? Now, after setting the length of the pendulum to the correct length, I want to start the first run of the experiment. So I'm going to displace the pendulum by a small amount like this. And then I'm going to start data collection. So this is what you see on the computer screen. Of course, the change is very small, so I have to click on auto scale in order to see clear view of what's going on. So as you can see, there is a wave form. Okay, so this is how the angle changes as a function of time. So basically, in order to get meaningful information from here, I have to add some sort of fit to this curve. Okay, so let's click on the curve fit and see what options we have. Now we have several options. If you go down by using this slide, just slide down. There is A sine BT plus C plus D. Okay, so I think this is the best that we can use with a curve like this one. So let's try fit. Now, as you can see, the black line lines up exactly or overlaps exactly with our experimental data. Now, from this fitting box, the box that corresponds to the line fit or the curve fit that we do, you can get the constant A, which refers to the amplitude of motion. You can get the constant B, which refers to the angular frequency of the motion, because it's B times T. Or you can get the phase angle, which is C. Okay. Of course, in our experiment, we're interested in the value of omega, which is the angular frequency. Now, after we're done with the first reading, we can move to the second reading by reducing the length of our pendulum by about 1 centimeter. Somewhere about 1 centimeter, around 1 centimeter, and then measure the new length. Again, from the center of the mass to the axis of rotation. Measure and record this value. And then repeat the same process again. So I'm going to displace it by a small amount and then start data collection. I don't have to start the motion and the data collection at the same time. I already started the motion. Just relax when you do this experiment and then start the data collection when you're ready. And this is set up so that it collects data for 10 seconds, so it's going to stop after 10 seconds. There you go. So here is my again data, so I can take the value of omega and then repeat the process for different other lengths. Okay. Now, in the second part of the experiment, we want to see what effect does the angle have on the period. Okay, so you can use any length of the pendulum. We don't have really to measure it. So let me use the full length again. Okay. So for the first run, I'm going to displace the pendulum by a very small amount, collect data. As you can see, when the amount is very small, because of the small angle of rotation of this sensor, it's a digital sensor, you get some sharp edges, but this is fine. When you do the curve fit, it's not gonna affect your results at all. So I did a small angle. Now I'm going to write the value of omega and then repeat the same experiment for the same length with a little bit larger angle, like this. Don't forget to write down the value of omega every time you repeat. You can also store the latest run all the time so that you have the data handy. Now, after done with this one, I'm going to write the value of omega in my lab report and then repeat with a larger angle. Repeat the same process. And then you'll find the value of omega from the fitting data and write it down in your lab report. Okay, you have to comment about the effect of the angle on the period and the frequency of oscillation.